So we have two models. We know that space is expanding, but is more matter appearing, in which case the universe always looks the same and we have a steady state theory, or is the amount of stuff fixed, in which case back in time the density will be higher, in future the density will be lower. That's what we call the Big Bang model. There's a very clear test of these two models. The steady state theory says the universe should always look the same, whereas the Big Bang theory says the universe should have an ever decreasing density. So in principle it's very easy to tell the difference. We just need a time machine. We look around today, see what the universe looks like, then go back in time a few billion years and see what the universe looks like that. If it was denser in the past, that's Big Bang theory. If it looks exactly the same, steady state theory. And luckily in astronomy we do have a time machine. Our time machine is light. We're sitting here on the Earth looking at things, but light just travels so pathetically slowly, a miserable 300,000 kilometers a second. That sounds pretty fast on Earth, but compare it to the huge sizes of space, that's pathetically slow. Even the Moon, which is pretty nearby, light takes 1.5 seconds to reach us from there. The Andromeda Galaxy, it's about 2 million years. And the most distant objects we can see are more like 12 billion years. So what this means is, when we look at the bits of the universe near the Earth, here's the Earth, the bits we see near it we're seeing more or less as they are today, whereas when we look at some part of the universe a long way away, we're seeing it not as it is now, but as it was in the past. So that's how we can, in principle, test our two theories. We look and see what the universe looks like in some local region, and we then look at some very distant region. And if this looks the same as that sounds like the steady state theory. If this sounds different, I mean it could just be because different parts of the universe are different. But if we see the same sort of difference if we look in this direction, and if we go to the same distance up here, and the same distance down there, then it's a fair bet that what we're actually looking at is not that this part of the universe and this bit are different, it's just that the universe has changed with time, which would be evidence for a Big Bang type theory. So let's do this. What do we see? Ideally, we'd like to look at the density and how it changes. Unfortunately, density is really hard to measure. We don't even really know the density of the universe today, at least not directly. However, the difference between the Big Bang and steady state theories is a bit more profound than that. The steady state theory says that everything should be the same. Therefore, if anything at all is changing, that's evidence for the Big Bang. So if anything is changing, anything at all, then the steady state theory is dead. So as soon as people developed good enough telescopes to see out large distances, they started looking for any sort of change at all. The first one that was spotted came from studying quasars. We'll come back to quasars later in this course. But basically, a quasar is thought to be a black hole in the middle of a galaxy, swallowing stuff. Stuff spirals in and falls into the black hole, it gets ripped to shreds, and intense radiation comes out. As I said, we'll come back to that. The point is that quasars are staggeringly bright, whatever they are. They can have a luminosity of up to 10 to the 15 times the luminosity of the Sun, which means you can see them at enormous distances. And what people were doing back in the 60s was plotting the space density of bright quasars against distance, which corresponds to time. This is today. No distance means the light hasn't had to travel anywhere. And this might be 13 billion years in the past. And what they discovered was something quite remarkable. There actually aren't very many quasars around nowadays, at least not the bright ones. But as you go back in time, they get much more common. At redshift around 2, there are about 2,000 times more quasars per unit volume than there are today. But then when you go further back, still the numbers drop off. So something is changing. Evidence for the Big Bang? Well, some people disputed this. It was only one sort of thing, and no one really knew what quasars were. In fact, we still don't. But then people started getting better and better telescopes, looking more and more detailed at what they could see, and other differences started to show up. For example, today, galaxies either look like flat disks, a little bulge in the middle, or they look like fuzzy balls, elliptical galaxies. If you look at galaxies out at about 10 billion light years away, a lot of the galaxies look like chains or strings or irregular collections of blobs. Quite different from galaxies today. But the real clincher was if you look far enough away from the Earth, so here's the Earth, far enough in any direction, you see a glowing wall. The universe seems to be opaque and glowing. You see it in all directions, incredibly uniform. And the light from it is actually in the form of microwaves coming towards the Earth. This is what's called the microwave background. We'll come back to that in the next lesson in much more detail. But that tells you that the universe today, which doesn't emit microwaves, was very different from the universe in the past when it was a glowing wall emitting huge amounts of microwaves. So the universe really seems to be changing. So steady state theory is dead. Sounds like the universe actually is decreasing in density, so it sounds like the Big Bang theory. There was a very hot, dense phase in the past.